Kindly mute yourself and this camera. Where is your camera? Okay. Good evening, everyone. This is our seventh session for this problem solving session for the course Advanced Power Electronics and Control, which is being taught by Professor Avik Bhattacharya. I am Adnan Farooq Khan and I am a research scholar at IIT Delhi. Like other problem solving sessions, in this session firstly we'll be having a brief review of what has been taught in this week, and subsequently we'll be moving towards the problem solving session. So coming to what has been taught in this week, there are like main okay, am I audible now? Like you can type in the text if you are having any questions or something. There is a chat window there, you can edit there. So I am Adnan Farooq Khan and today we'll be having seventh problem solving session for the course Advanced Power Electronics and Control, which is being taught by Professor Avik Bhattacharya from IIT Roorkee. And like every other problem solving session, firstly I'll be going through what has been taught in this week, having a brief overview of the different concepts like that were taught by the sir in this week, so that you could get an idea about solving different numericals and all. Like this is only to brush up what has been taught in this week. Like there are different topics that were covered in this week, like space vector, PWM, AC to AC converters, and subsequently cycloconverters was taught, and matrix converter. I'll be briefly going through these topics to brush up what has been taught in this week. Then we'll be moving towards this problem solving part. So coming to the space vector PWM, like we had discussed in previous sessions about like three-phase inverter. Here we have three-phase PWM based inverter where we have a constant DC source, and from this constant DC source what we want is a three-phase AC. In this thing, as you can see, we are having a three-phase inverter which comprises of like three legs. You can see they're named A, B and C, which will comprise out three phases of a balanced three-phase system. So AO will be our load phase voltage, VBO and VCO subsequently for the B phase and the C phase, which will be phase shifted from one another by 120 degree. Like in the previous week, what was being taught is like we saw how we will operate this three-phase inverter, and we had seen sine PWM modulation technique for this three-phase inverter, by which we will be able to generate three sinusoidal voltages at the output. Today what we will be going through is like space vector PWM, which has already been taught. Like this is just to brush up the idea that how this space vector, this is another modulation technique to generate these sinusoidal voltages at the output. So as you can see, before going towards the space vector modulation, here you can see, as we have in each leg two switches, we'll be having like two switch states like that are represented by P and 0 or O. Whenever we are having a P switching state, that means the top of the top switch is on in a particular leg. Let us say we have this A leg, and the switching state in this is P. That means S1 will be switched on and S4 will be switched off. Similarly, if for the second leg, if we are having a zero state, that means S6 will be turned on and S3 will be turned off. So if any of the top switches is on, that will be represented by P, and if any of the bottom switches is on, that will be represented by 0 or O. And we know for each of the leg, the switches will be turned on in the complementary fashion. That means only one of the switch will be on at a particular instant, either the top one or the bottom one, because if both of the switches are turned on, that will short our DC source, and which can damage our source or the converter. So being this, like if we are having a zero state, then means we'll be having a zero voltage at the pole. VAN will be 0. For each leg we can have like two voltages. If the top switch is on, we can have VAN will be equal to VDC, and if our bottom switch will be on, that means VAN will be equal to 0. So as we have three legs here, 8, like their total number of switching states that will be there will be 2 raised to power 3. That will be a total of 8 switching states will be there. We'll be seeing like these different switching states that will be there. So the different switching states that will be there are like, we'll be having like 0 0 0 switching state. 0 0 switching state means like for each of these three legs, all the bottom switches will be on. That will cause that we will be having a 0 voltage at the in these phases, or our port voltages will be 0. In a similar way, if all the top switches are on, that is 1 1 1, we will be having a 0 voltage at that time as well. And subsequent switching states will be like P00 or POO. That means for the first leg, S1 is on, and for other two legs, S6 and S2 on. And subsequently we'll be having a switching state of P and O. That means the top switches like S1 and S3 will be on for leg A and leg B, and S2 will be turned on for leg C. In a similar fashion, like for 0P and 0, we'll be having S4, S3 and S2 on, and for 0PP we'll be having S4, S3 and S4 and so on. Here you can see that we are having like 2 zero switching states and 6 active switching states. That means in case of like PWM, 3-phase PWM, we'll be having a 2 zero vectors and 6 active vectors. I'll be coming to this, what these vectors will be, like 2 zero vectors and these active vectors. So as you can see here, we saw different switching states that will be there. We can represent like each of the switching state as a vector. How this vector comes out, that we'll be seeing in the next slide. So if you can see, like if we are having a zero vector, that will be represented, firstly coming to that, if we are having sorry, if we are having like a balanced 3-phase system, for a 3-phase system, we know we can represent this 3-phase by a single vector, and by this transformation, that will be like all of our 3 phases, VAO, VBO and VCO, which are like these phase load voltages. This can be represented by a single vector that we call as Vref. Let us say Vref. It can be called by this transformation. Like this transformation has been taught you in detail during the course, and you can look about the derivation of this transformation. When we are able to like transform this these like 3 vectors in a these 3 phases in a single vector, we can represent this, like this Vref will correspond to our different like location of this resultant vector that has been developed by the transformation. So like we saw different switching states. If we are having any of these zero switching states, that means PPP or 0, 0 or 0, that means the amplitude of our vector will be 0. And now if our switching state is POO, that means this is on and these two are on. If we put up the values of here, this is like you will see that this Vref will align with this 0 axis, and the amplitude of it will be like 2/3, and this will be equal to maximum amplitude. Similarly, if we have a switching state of PP and 0, that means if we put like S1 and S3 will be on and S2 will be off, we will get a vector that will be at a 60 degree, that is represented by this line, vector 2. Similarly, if we have a switching state of 0P and 0, here you can see only the B vector is on. We see when only A vector was on, it was like aligned with the 0 degree, like an A phase, and when only B is aligned, it will be at 120 degree from the A, that it will be represented by V3. In a similar fashion, if we have like 0PP, like B and C vector, we will be getting this vector that will be 180 degree line. And in a similar fashion, if we have only 0, 0P, that means only a C vector is on, like of the C line, and these two are bottom, or 0, 0, like S4 and S6 on S5, will be getting a C vector that will be, if you can see, that will be 240 degree shifted from the A and 120 degree phase shifted from B. In a similar fashion, like this at an angle of like minus 60 degree, you can see we are having like POP, or if our switching state be POP, like if we switch between this vector and this vector for equal amount of time, we'll be getting this vector, that is vector 6. So you saw, like if we have we can get any of these 6 vectors in a space, like by appropriate switching of any of these devices like S1, S3, S5 and S4, S6 and S2. But by properly switching these devices, we are able to attain only a certain space vector in a certain position, like that of 0, 60 degree, 120, 180 and so on. But if we want to have our resultant at a different position, at any of the position, like in any of these sectors, you can see we have like represented these different sectors as sector 1, sector 2, sector 3, sector 4, sector 5 and sector 6. You can see they form like a hexagon kind of a thing. But with these switching states only, we are able to attain only these these vertices of this hexagon. But what if we want to have a reference at any other point in any of these sectors? How can we have that? Let us say we are having a voltage reference in sector 1 and we want to how we will achieve that in at any other position other than 0 and 30 degree. What we will be doing at that time is we will be switching vector v1, v2 and 0 vector for appropriate amount of times, so that any position can be attained for this vref. That we will be seeing how we will be doing that. Like this is the transformation. So like if you can see, if we that I had already discussed, if we can see that if we are having a top 3 switches on and bottom 3 switches on, we'll be getting a V out that will be equal to 0 degree, and if we have only P that I have shown, like we'll be getting 2 by 3 VD at an angle of 0, and so on. If you can see that I have already discussed, this is I have tabulated in a table for different vectors and positions. Now coming to the part how we are going to attain like these positions. Now we want to see if we want to have, let us say here I have taken an example of a sector 1. Now I wanted to have the resultant vector, this vref, at any position other than that of this v1 and v2. What we will be doing, we will be switching this v1 for certain amount of time, let us say that will be t1, that will be given, and v2 for a certain amount of time, v2, and v0 for a certain amount of time, t0. So like vref into ts will be equal to, like we'll be switching v1 for t1 amount of time, v2 equal to t2 amount of time, and v0 equal for t0 amount of time. If you can see here, like this the point Q is the if you can see, if this vref exactly lies at the center of this line between the v1 and v2, that means we have to switch v1 and v2 for the exact amount of time, so that this v reference will be at the center. Now if we want to have vref towards this v1, that means that we will switch v1 for more amount of time than v2, that means t1 will be greater than t2. Now if this vref is towards this v2 vector, that means we have to switch v2 vector more for more time than that of the v1 vector. That means at that moment of time t2 will be greater than t1 vector. Now if this vref aligns with v1, that means at that moment of time t2 will be equal to 0 and t1 will be greater than 0. That means we won't be switching the v2 vector at all. What will be switching? We will be switching the v1 vector only. Similarly, if this vref is aligned with this v2 vector, at that time we will be switching v2 vector only, and the v1 vector we won't be switching at all. That means v1 will be 0, like t1 will be 0 at that amount of time. So here, like, but we know, like, this t naught is the vector for the 0 vector time for which the 0 vector is switched. But we know, like, we are having two 0 vectors that are determined if we are turn all the top switches or all the bottom switches. So what we can do is, what we do here is we divide this, like, 0 interval in two equal halves. That for half of the portion 0 0 0 vector will be on, and for other half, like 1 1 will be on, so that we have an equal distribution of losses, or bottom and top switches switch on for the same interval of time. And I'll be showing you, like, how we will be switching in, like, different, how we'll be doing the switches in different intervals. So our switching time, total switching time, will be equal to time for which we will be turning on the v1 vector plus the time for which we will be turning the v2 vector, and the time t naught for which we will be turning the 0 vector. And like I told you, like, t01 and t07 will be equal to ts by 2. That will be equal to, like, that is the half of this, the time period for which the 0 vector is turned on. Sorry, here is a mistake. It is t0 by 2. t01, t0, it will be equal to t07. That will be equal to t0 by 2. That is the half of the interval for which the t0 vector is turned on, and not the switching time. So now we saw, like, if we want to have any position of this resultant vector, we can switch on. But now we want to see how we will be having this switching sequence. Like, we can have any of the switching sequence. You can first switch on this vector, and this vector. But the right way of doing it is like how it is showing here. What we want here is, we want to have minimum switching changes in one switching time. Like I'll show you, like, if we will first start from 0 0 0, like this vector, then we can move towards, like, first we'll be switching this 0 0 vector for a certain amount of time, then we'll be switching p0 0. That means we'll be switching then v1, and after that we will be switching p0. That means after that we will be switching this v2, and after that we will be switching p. Then again we will be switching 0 vector for some amount of time, and after that we will be switching, we won't be switching v1, we will be switching v2 back, and then v1, and then v0. If you can see here, between this there is only one single change. That means, like, at any moment only two switches are getting there is a position of the switches, for two switches are changing, like one of the switching is getting turned off and other of the switching is getting turned on. If you can see here, there is only one switching change here, only one switching change is happening, that is with this A phase, like A phase is getting turned on. If you can see here, now the A phase is on, like now B phase is getting turned on. Now let us say after 0 0 0 I would have switched V2 first. Then what would have happened is, like, first it would have been 0 0 0, then it would have been PP0. You could see we would be having two switching changes in two of the legs. That means, like, there will be two changes in this, like 4 of the switches will take part in that. That will would increase our losses and all. What we want to is we want to minimize the switching changes. That is our motive. Like we want to have the switching sequence in such a way so that we will be having like a minimal switching changes in an interval. If you can see, after pp0, if you do ppp, there is only one change, like this 0 is going to p, and subsequently you can see that pp0, that means only one change is happening as p is going to 0, and so on. There's another we can do it. We can have ppp, then we need to have pp0. Like first we could switch one vector, like 111 vector, or like then we can switch v2 vector, then we can switch v1 vector, then 0 vector, and then v1 vector, v2 vector, and again the 0 vector. Ultimately what we have to keep in mind is we have to minimize the switching instants. This was about like you can go through the lectures and you can see the derivation of these like time intervals, the formula that comes out like to be for these t1, t2 and t0, that has been taught in detail in the course. For that like you consult like what here I wanted to give you the idea like what has been taught and what this space vector modulation is all about, how you'll be generating these pulses for our switches in the three-phase rectifier. So what other things were taught in the other topic that was being taught is like AC to AC converters. Like firstly we had seen we had a like a rectifier, we had AC, then we had a DC here, like we were rectifying it. But now what we want to have an AC to AC conversion. Like we have an AC input and at the output we want AC as well. And how we want to like achieve that? The basic like circuitry will be having a single phase AC to AC converter. Like for when we have a positive half, then that at that time S1 will be turned off. Like we'll be having a two thyristors S1 and S2 in an anti-parallel fashion. That means during the positive half S1 will be turned on, and during the negative half S2 will be turned on. And when we'll be having during the positive portion, when S1 will be turned on, we'll be getting the positive half, and there will be an S1. Let us say this Vs represents the input. Now we want to have our output. We know these thyristors, with these thyristors, like we can these are control device, and we can turn on these thyristors at a certain instant. Let us switch on this thyristor if S1 is turned on at a degree alpha. That means this S1 will start conducting from this position. When this S1 is turned on at this moment, that means after this it will start conducting. We will be getting at the output some voltage, a part of this voltage, that is this voltage from alpha to pi. Had this alpha been equal to 0, we would have got whole positive half cycle at the load. Now if when the voltage is negative, so if we don't have this thyristor, or if we have this thyristor and it is turned on at pi only, we'll be getting a whole negative cycle at the output. But since this thyristor is turned on at pi plus alpha, so it will start conducting at pi plus alpha, and we'll be having a negative half at the output to the to pi. And after that subsequently it will follow the same pattern. Like the S1 will then start conducting again, and we'll be getting a positive half, and this is the voltage blocked by the switch till it is turned on. Like this is the positive half of the voltage up to this point will be blocked by this switch. This was about like the single phase circuit with the RL load. Here you can see, since the load is like resistive, that the shape of the current will be same as that of the like voltage, and When this voltage will go to 0, the current will also go to 0. uh, Now we'll see, had there been an up to this point we were seeing it for an R load. Now we would want to see what would happen if we will be having an RL load instead of an R load. So like we saw in this previous classes, like whenever we are having an RL kind of a load, if we, let us say, turn on this S1 at an alpha, so what would happen, this S1 will start conducting from this alpha. So when S1 starts to conduct, the load, in the load current, there will be some energy that will be stored in this inductor, or uh, there will be some voltage V will be equal to LdI by dt, that is across the inductor. And when this voltage, source voltage, comes to 0, had this been an R load only, what would have happened? The current would have come to 0, and after that S2 would have been turned on. But we know with an RL kind of a load, we cannot interrupt the current that is flowing through this inductor. So when this voltage goes to 0, this S1 won't turn off, and it will still start to conduct. However, be it so that our voltage is negative at that moment of time, but we know from the equation VL is equal to L di by dt that this current cannot be interrupted through this inductor. This means that this current will still flow until it goes to 0. That means we will be getting a portion of the waveform that will start from the alpha until this I out goes to 0. But we had seen in this with the R load, with AC to AC converters, when this current at the alpha, when S1 started to conduct, I out was going to 0 at the moment that voltage was going to 0. But that is not case with this RL kind of a load, because due to this inductor which will store some amount of energy, I out will go at an angle, let us say beta. So we will be getting our output voltage up to this beta point. After that, this voltage, output voltage will be equal to 0, because none of the devices is conducting. After that, at pi plus alpha, when we'll be turning on this S2, we'll be getting a negative portion at this, at the load, at this load, you can see, and that is here. And similar thing would happen, that current won't go to 0 at this. When this negative voltage go to 0, it will start to it will still conduct up till this output current comes to 0. So our load voltage be sort of this kind of a wave that will be from alpha, that will be having a V out we'll be having alpha. If anyone of you has having the question, like, he can type it in the chat. So it will be having the waveform from alpha to beta, and in this portion only will be the switch will be blocking voltage, and this will be the voltage that will come across the switch. That is the waveform for the switch voltage. In a similar fashion, like this was for the single phase, coming to the three phase, here what we have is, we will be having this kind of a setup for each of the phases, and the operation is same. Like if we want to have a positive half of a certain phase, like we'll be turning the S1, and for the negative half we'll be turning the other device, and so on for the other phases like A, B and C. And regarding the waveforms, you can go through the lectures. The idea is the same like of this single phase single phase AC to AC converter, and you will be going through the waveforms that have been taught, like with different with like diff, different alpha, like we can have different kind of a voltage. Like other AC to AC converter is, we have a cyclo converter. Here you can see we are having a like a single phase cyclo converter. So this single phase cyclo converter comprises of like a two H bridges. You can see here where we are having like uh, they are connected in such a way. You can see that whenever this P converter is like P, we are having like a two converters P and N, they are connected in such a fashion, and we are having a same source Vs that is connected between these points. You can see this point, and this point, and this point. So whenever P converter is conducting at this across this load, we will be getting a positive voltage, and whenever this negative is converter is conducting, we will be getting a negative voltage at across this load. So let us say we are having a source of 50 hertz like this. We are having a source of like a 60 hertz source, and we want to have like AC across this load of some other frequency. Let us say we want to have this AC of around, let us say, 20 hertz. So what this cyclo converter does is, it does an AC to AC conversion, where we have like generated the AC of of different frequencies. Like in our drives, if you want to have this V by F control, you want to change the frequency. This is one of the converters by which we can have AC, and we can generate a AC of some other amplitude frequency and amplitude. So for the positive half, this P converter will conduct, and for the negative half, this N converter will conduct. So whenever this P converter is conducting, and we can see we will be getting this positive voltage. Let us say we are turning on this T1 and T2 at 0 interval, and it will start conducting from the 0, and we will be having, if we want to have this frequency 1 by 3 times, let us say we are having a frequency of input of a 60 hertz Vs, and we want to, at the output, we want to have a voltage waveform that is of the frequency of 1 by 3 times of this 60 hertz. So what we will do, we will like have 3 positive half cycles, and after that what we want to do is, we want to have the negative voltage. For that, we will be turning off this P converter, and then N converter will start conducting. And if these if we give the gate at the 0 interval only, then we'll be getting the whole negative part as a whole. But as we're talking about this alpha, we will be triggering these converters. If we have an alpha, so we'll be getting this negative part. So if you can see that we are having the 3 positive pulses and 3 negative pulses, you can see we'll be having a fundamental that will be in this voltage waveform, that will be of the frequency 20 hertz. That means, like, for the positive half, this P converter will be turned on. For the negative half, this N converter will be turned off. Like this positive, that means that the positive current will be conducting through this P converter, that will flow through this converter, and N will be flowing through this. You can see via this, and this, because like negative converter, negative current cannot flow through this converter, as we know that these thyristor are only like unidirectional in terms of the current carrying conducting capabilities. It can block both voltage positive and negative, but it can only conduct current in a particular direction. Also, another thing that I would add here is, like, If we trigger this P converter at an angle alpha, then the N type of the converter will be triggered at an angle pi minus alpha. So if this is an alpha, so the triggering of this at this triggering of this N part will be pi minus this alpha portion. So we will be triggered the N converter at this pi minus alpha degree. That is one thing that we need to remember. If we are triggering the P converter at an alpha, the N type of converter will be triggered at pi minus alpha. This was about the single phase cycloconverter. Similarly, we'll be having the three-phase cycloconverter where instead of only like one HP here, we are having like a three legs. Like we'll be having an input of three phases, and across this load we'll be getting as per our switching and this triggering will be getting a three-phase voltage of different frequencies. It is a similar kind of a back-to-back converter where we'll be having a P type and N type, and during the positive half on this P side will conduct, and during the negative half, like in a similar fashion I explained here, in a similar fashion it will conduct here. Like the positive current will be conducted by this side, and negative current will be conducted through this side, so that we'll be getting a positive voltage across the load if when this converter is turned on, and negative when this converter is turned on. The other type of a converter that was discussed was like matrix converter. What we have in here in the matrix converter is also like a direct AC to AC conversion. In the matrix converter, where we having three phases, and we are having a switch configuration in such a way, like we are having like a 9 bidirectional switches. You can see we are having the 3 bidirectional switches in each phase, like S, A, B and C. When we are having like three in a similar fashion, we have 3 switches in the B phase and 3 switches in the C phase. So the idea here is like we should be able to connect this A phase can be connected to any of the output phases. So if we'll be like, let us take A, if we want to connect it with A phase, then we'll be turning this switch on. If for B, then we'll be turning this switch on, and for phase C we'll be turning this switch on. And similarly for other like phases, we'll be turning on the switches as per our need in a similar fashion. So with like 9 bidirectional switches, the total switching combinations that are possible is 2 raised to 9, like that is around 512 switching states. That are a lot of switching states, but we can rightly eliminate many of the switching combinations. Like we don't want to like turn on 2 switches in one leg such that like we will short our, if we like turn on this and this, like we can short our source. So what we have to keep our mind that only one switch in one leg should be turned on at one moment at an particular instant. If we turn on like let us say 2 switches like this switch and this switch, you can see we will be shorting our source. Also if we like turn off all the devices, like we'll be opening our load, that will be some inductive load at the output, like we have to keep in mind we cannot interrupt the inductive load at any instant. So yeah, with these things in kept keeping in mind, what like these 512 switching states get reduced to 27 switching states only. And you can see how what are those switching states and how we will be switching for like a certain instance, and how we will like have the different output of different frequencies, and how this is done. That has been taught in detail. in the course you can refer to the lectures. Like here it was like briefly I had to give you the idea what this matrix converter that was taught is. So yeah, this was about the uh, what had been taught in this week, like space vector. We discussed about space vectors, like what are the different switching states that are possible in the three-phase vector, like representation of this vector in a plane, in a space, for certain positions, and what are the different, how can we attain this vector at different positions, how we will be switching different these. Then we moved like AC converters, and then towards this matrix converter. So yeah, this was about the topics that were like discussed during this week. Now I think uh, I'll be taking a break of like 5 minutes, then we can move towards this problem solving session. I think uh, some of you are there, like in the meanwhile you can start solving if you can solve this question, and I'll be back in 5 minutes and you can solve this question. So yeah, can continue like with the problem solving. So this is the first problem. A single phase half bridge inverter has an RLC load. The DC input voltage Vs is 230 volts and the output frequency is 50 Hz. The expression for the load voltage up to the fifth harmonic will be given by. So there are like a number of options that are given. We can see the first option, it has the fundamental, second harmonic, third harmonic, because like if you can see this output frequency is given as 50 Hz. So you know like omega will be equal to 2 pi into 50, that will be equal to around 314. So you can see omega is 314 in all of the options. Now we have to see which of the options is like correct. So in the option 1 we have the first harmonic, second, third, fourth and fifth harmonic. In the option second we have the first harmonic, third harmonic and fifth harmonic. And in the option C we have first, second and fourth harmonic. And option D is none of the above. So we know that with the half bridge inverter, if we have like this is a half bridge inverter, the output voltage we will be getting, if we turn on S1 we will be getting VDC by 2, and if we will be turning the S2 we will be getting minus VDC by 2. So we know that in a half bridge we will be getting at the output voltage waveform is a square kind of a waveform. Now we are having, moving forward, this was for like we have seen in the previous like classes. Now when we have this square wave, so we know when we have this square wave kind of a waveform, and if you can see this waveform has a half wave symmetry, and if we do the Fourier analysis of this square wave, you will see there won't be any even harmonics in this. Whatever there will be only odd harmonics. So the even harmonics are right outly like eliminated. That means the first option and fourth option is not the correct one, because we are having even harmonics like 2 and 4. That leaves with this option B and D. Now we will see what will be. So we know like the VO can be represented as a summation of 2VDC by n pi sine n omega t. This is the peak value and this will be the subsequent harmonics. So we will see what will be the peak value of like this 2VDC by will be given by for the first harmonic, that will be 2VDC by pi. We know the VDC is given by like 230 volts, and when we have a 230 volts and this 2VDC by pi comes out to be 146.42 volts. Also, like I earlier told, we have omega that will be equal to 2 pi into 50, that will be equal to 314 radians per second. Also you can see when you will do the Fourier analysis that the subsequent harmonic amplitude of the subsequent harmonics will have the amplitude divided by the number of the harmonics. Like for the third, there like we won't be having any even harmonics. For the third we'll be having the amplitude of 2VDC by 3 pi, and for the fifth we will be having an amplitude of 2VDC by 5 pi. So the amplitude of the first one is 146. If you divide that by 3, we'll be having like 48.8, and if we divide further like this 146 by 5, we'll be having a 29. That is the correct option. Like for the question number 1, we will be having the option of B is the correct option. Now coming to the question number 2. The question number 2, what is asked here is, in voltage source inverter we have like different options. You have to like choose which among us them is the correct one. It is given like both voltage and current depend on the load impedance. Also, like what is given is only voltage depends on the load impedance, or only current depends on the load impedance, or none of the above. Can any one of you like guess what can be the correct option? So one of the options, like one of your students has answered is on C. We'll be seeing what is the correct option for this. Let us first go through what is how this voltage source inverter will look like. So as earlier, like for the one leg, we know we are having a converter, like let us say this is VDC, and one leg is represented by S1 and S2 switch. Here VAN will be like a, let us say, load voltage. This is sort of a half bridge. So we have a constant DC voltage. That means like this input is constant, and we have two switches, S1 and S2, and we know that we cannot turn on the both switches simultaneously. That means like we will be shorting the source. So we know that these switches S1 and S2 are turned on in a complementary fashion. That means when S1 is turned on, we will be getting a VDC at the output, and when S2 is turned on, you can see we'll be getting A and N will be at the same potential. That means at the output we'll be getting zero voltage. That is what is given here. That when S1 is on, we will getting a VAN will be equal to VDC. And when S1 is off and S2 is on, like this A and N point will be at the same potential, and this VAN will be equal like 0. So now coming to this single phase VSI, like a full bridge, what we'll be having, we'll be having a single phase VSI. We will be having a like a sort of a H bridge kind of a structure, like we saw. We'll be having a VDC, and between VA and N we'll be getting an AC kind of waveform here, that will be like a square wave A between A and B. How this is operated, like we will be turning S1 and S2 simultaneously and S3 and S4 simultaneously. Also what we want here is like these switches should be bidirectional. That means they should be able to conduct this negative current as well. So when S1 and S2 are turned on, that means we will be getting this A point will be at DC and B point will be at this negative potential. We will be getting a voltage of VAB will be equal to VDC, as you can see here. And when this S3 and S4 is turned on, you can see B point is at a positive potential and A point is at a negative potential. That means this voltage will be VAB will be equal to minus VDC. As you can see, this VDC is like a stiff voltage. That means this cannot change, and whenever we will be doing a switching in this position, we will be getting a similar kind of a waveform, VAB. However, we know that whatever current that will be flowing through this load will be dependent on this load. However, how our load would be, let us say this load is resistive. Just a minute. Let us say this load is resistive. When this load is resistive, we know at that moment our current will be similar to that of the voltage. That current will be positive when this will be like a plus VDC, and current will be negative. That will be having a positive amplitude and a negative amplitude. If our load is an RL kind of a load, we know we'll be having this sinusoidal kind of a waveform, and it will be lagging by some angle. You can see when this voltage is positive, we have a negative current. That is why we have a, let us say this is a positive direction, then the current will be flowing in this direction. That means this S1 and S2 should have the bidirectional current carrying capability. And similarly, if we are having a RLC load, we'll be having a sort of some kind of a wave, like of a sinusoid of a similar shape, uh, kind of a shape. That means here you saw, depending upon this load, our current waveform shapes are getting changed. That means our current depends upon the load impedance, not the voltage. Here we saw that voltage is also stiff and it doesn't depend upon the load. Howsoever be the load, the voltage will have the same square kind of a shape. But if but our current depends upon the load. If our load is resistive, we'll be having a square kind of a wave. If it's an inductive RL kind of a load, we'll be having a, if there is a purely inductive, will be having a sinusoidal RL, that this will be some sort of a wave, kind of a waveform that will be of a sinusoidal shape. That means that you saw with the change on the load impedance, our current shape is getting changed. That means like option C is the answer to this question. Now comes question number 3. A cycloconverter is which type of a converter? First option is like one stage power converter, B is one stage voltage converter, C is one stage frequency converter, D is one stage current converter. Can any of one answer? Anyone? So one of the students has answered is like C. Like I discussed in this cycloconverter, what we want to have with the cycloconverter, if we are having a source with some frequency, I mean if we want at the out, and we want to have the variable like AC with a variable frequency, like at the output we want to have this AC waveform but with some other frequency, what we use is a cycloconverter. And we know, like here is saying one stage, as you can see, like I had shown you here, this is a single stage. Like this, here we have an AC and it directly converts it to AC of some other frequency. Like let us say here it was 60 and this is 1/3 of, like we at the output we got an AC that is of 20 Hertz. And we had only one stage, like we do a direct AC to AC conversion. Other thing what we can do is, if you have a, like let us say this kind of a thing, not here what it's saying, it is like a DC to AC inversion. Let us say first we'll be doing an AC to DC, like a rectification. We'll be having an AC of some frequency and we'll be converting that into DC. And after this DC we'll be having an inverter stage like this stage, and before this DC stage we'll be having a rectifier stage, and we will be first converting that single phase AC or three phase AC to DC, then we'll be converting them to the subsequent single phase or three phase DC, three phase AC by a single phase or a three phase inverter. In that, what you can see, two stages are involved. Like first we do AC to DC, then we do DC to AC, and we can have with our modulation, like with the DC to AC conversion, then we can have like at the output we can have the ACs of different amplitudes and of different frequency as per our need by changing the modulation wave and modulations. So the here with the cycloconverter, like I discussed, like it is a direct frequency change. Like we have some AC with some frequency in the input, we can have a single phase or a three phase cycloconverter, like I discussed in the revision part. Like we can have some input with one frequency, at the output we'll still get an AC with some other frequency. That means it's a direct AC to AC conversion, where we convert an AC of one frequency to the AC of some other frequency. That means option C is the correct answer to this question. Coming to the question number 4, in three-phase cycloconverter, the reduction factor is given by. So here are different options: input frequency by output frequency by input frequency, C is input frequency by output frequency raised to power minus 1 by 2, and D is input frequency by output frequency raised to power 1 by 2. So one of you has answered this B. I think this wasn't like the reduction factor is like given by, in the cycloconverter, the formula for that, what is given by it is the output frequency divided by the input frequency. So what is the change between the frequency of the output to the input? If we are having an input source of some frequency, and we are having an output and we are having an output maybe of a frequency that will be certainly be lower than that of the input, because we will be like turning on our p-type or n-type for certain amount of time, where we will be allowing, if we want to have 1:1, at least we will be allowing for p-type will be turning on for the positive half and n-type for the negative half. And if we turn it for 2 half, that means the output frequency will always be like lesser than that of the input. So yeah, like this factor will always be less than 1, I think. So now coming to the question number 5. So question number what is asked in question number 5 is, a single phase bridge type cyclo converter has an input voltage of 230 volts and 50 hertz, and the load of like 10 ohms. What is given is output frequency is 1/3 of the input frequency. So we have an output frequency that is 1/3 of the input frequency. So what we can see, for a firing angle delay of 30°, calculate the RMS of the each converter. We have to calculate the RMS current of the each converter. Like we have seen for the single phase cycloconverter, we had like two converters. One is like a p-type converter which conducts during the positive half, and we have a n converter which conducts during the negative half. You can see like here we are having like thyristors in the p half. They will only conduct the positive current, and the negative current won't be conducted by them, that will be blocked by them. And you can see in the n converter, the negative current is conducted will be conducted by this n-type converter and not the positive one. So during the positive half, p-type will be conducting, and during the negative half, this n will be conducting. And as I had like discussed, some of you might have joined late, and as I had like discussed, the triggering of this, if triggering of the p-type converter is at an angle alpha, and where we will be triggering our n converter will be at pi minus alpha. So if this p type is triggered at an alpha, the n will be triggered from pi minus alpha, that is from this point. Also, what is to be kept in the mind, the average of the voltage of this p converter and the n converter will be same, but the it will be negative, the signs will be negative. So the voltage that will be, we can have like any amount of average by changing this alpha, and this p will be having a positive, and by p will be having getting the positive voltage, and with this n converter will be getting this negative voltage. The amplitude magnitude of them should be same. The average instantaneously it can differ, but average should be same, but of the opposite polarity. So, and if you like calculate the RMS of with this alpha, if you can calculate the RMS of this wave, then you will see it comes out to be like the equation that comes out to be V out will be equal to RMS will be equal to Vs 1 by pi minus alpha sine to alpha by 2. Here alpha is the triggering angle, and we know that alpha Vs is given to us, that is 230 volts, and alpha is like 30 degree, and if you put the value here, it comes out to be 226.66 volts. That this will be our RMS voltage. So what we had to like calculate is RMS of the current. So when this we got the RMS output voltage, we got out to be this. So output current, since our load is resistive, it will be equal to I out will be equal to I out, it will be equal to V out by R. So our R is like 10 ohms, so this will be equal to like 22.66 amps. And the equation for like this IP, we know that IP and IN have the same magnitude, but only the direction is opposite, so that will be equal, and RMS of that is given by I out divided by root 2, and if you like divide this I out by root 2, it comes out to be equal to 16.027 amps. So the 16.027 is like, that is approximately equal to 16.03. That means option D is the correct option for the question number 5. Just a minute, sorry. Yeah, moving forward. Now we are having a question number 6. Here what is giving, a single phase bridge type cycloconverter has an input voltage of 230 volts and 50 hertz. Like it's similar to the previous question, but here something else is asked. And the load of R is that is given as 10 ohms. Output frequency is 1/3 of the input frequency. For a firing angle of 30 degree, calculate the input power factor of the cycloconverter. Previously what we had calculated is the output voltage and output current, and now what we want to calculate is like input power factor. So like previous, it is similar, concept is similar to the previous one. We'll be having the p type and n type converter. Well, p will be conducting during the positive half, will be getting the positive halves, and n will be conducting during the negative half. So power factor will be given by P out by, we know the power factor is given by P out by Pn, like it will be P out Ps into Is. So P out will be equal to V out into I out into cos theta, like that will be the phase between the voltage and the current. But since here we have a resistive circuit, we know the load is resistive, that means cos theta will be equal to 0, cos theta will be equal to 0, cos theta will be equal to 1. So we will be having P out will be equal to V out into I out for our load. Also, if you can see, if you see this cycloconverter, we know that this source current will be equal to the load current, because we have this source current, like it will have this same shape as that of the load current, because we are doing an AC to AC conversion here. So that means Is will be equal to I out. So if you can see, we will be having Vs into I out, like P out will be equal to V out into I out, and you can see that will be get cancelled, and power factor will be equal to V out by Vs. Now we know Vs, like that is 230, but how we can calculate V out? That we saw in the previous example, like V out will be equal to like Vs into 1 by pi minus alpha, and this thing, this will be equal to the V out. So when we divide this 226 by 230, the power factor comes out to be 0.9855. So you can see that the option C is the correct option. Like a single phase bridge type converter with have a power factor of this when this is given like 0.98 will be the correct option to this question. Now coming to the seventh question. Seventh question is asking a three-phase to single-phase cycloconverter employs three pulse positive and negative group converters. We have like a cycloconverter with three pulses. You can see like a three-phase half bridge. You can take into the consideration. Each converter is supplied from delta star with per phase. We have it. They are supplied by transformer with a transformer turns ratio of 2:1. The supply voltage is 400 volts and 50 hertz. And also what is giving is we have a load RL load of like 2 ohms. We're having a RL load of 2 ohms is the R portion, and at the low output power frequency we have omega naught L, like L part will having an impedance of like 1.5 ohm. In order to account for the commutation overlap, the thyristor turn of time, the firing angle in the inversion mode should not exceed 160 degree. Find the value of fundamental RMS output voltage. We have to see what the fundamental value of the RMS voltage will be equal. Like there are certain, like we will be solving this question. Like I told you, we are having a three pulse converter here, you can see, but we are doing three phase to single phase conversion. So we'll be having a sort of a like a three phase half bridge sort of a structure. Will be having a positive group or a p type or negative group that is given by the n type. You can see here, whenever there will be a positive like voltage will be conducted, whenever there is a positive voltage, like this positive group will start conducting, and whenever there will be a negative voltage, like this negative group will start conducting. Also you can see here that whenever there is a positive voltage, that will be conducted by this positive group, and whenever there is a negative voltage like this way, that will be conducted through this negative group. So now we'll see, like when we are having a three phase voltages here, depending upon the like alpha or any triggering angle, we can have different. If you can see here, like with respect to different alpha, like we can have like different these voltages, instantaneous like voltages, and if we having like this kind of a shape, actual shape. But if you can see the over this like kind of a waveform with this three phase, like we are having like output voltage input voltages, this is the actual voltage that will get fabricated like this. If you can see how my this cursor is moving, depending upon our alpha, this will change. And you can see if you take the mean of it, or what it will have some fundamental which will be of some other frequency than that of the input, because we are doing an AC to AC conversion, and we know we will be having at the output some lower frequency output of some lower frequency. And if you can see the mean output voltage, and you can see that is sort of a sinusoidal wave. This is our voltage, and what we'll be having at the output, we'll be having some output current that will be flowing through the load. If our load will be resistive, then our like voltage current will be in phase with the fundamental of this voltage. But if our loads are something like RL load, then we can have like our lagging sort of a current. Also what we can see, like we are having these two positive and negative groups. So here we can have like a different kind of operation, like that as he shown here, like an inversion, rectification, then again inversion, then rectification. You can see whenever our this voltage is positive, whenever you can see not only positive and our current is negative, whenever we are having voltage of and currents of different signs, like you can see here voltage is positive and current is negative, you can see we are having a negative power. You can have see like we are having an inversion kind of an operation, and whenever there are same polarity like positive and positive, we can say it is of the like we are having a positive voltage as well as positive, and we can say it is a sort of a rectification. Similarly here you can see that voltage is negative but current is positive, still we are having an inversion sort of a operation. Here we are having a negative voltage and negative current, we can see we are having like a rectification sort of operation. So what we have to remember is we have to have, like if we are having a voltage and current of different polarity, we are having an inversion operation, and if we are having the same, we are having a rectification operation. And the like for the output waveform in this kind of a topology, like if you go through the nodes, like it is given by this equation: V out will be equal to R into V phase M by pi. Here M is the topology given by the number of like pulses, like here we are showing like the 3 pulses, so M will be equal to 3. What is this R? Like R is the factor that is known as the reduction factor, so that is given by R will be equal to cos phi m. And we know like here it is given like negative should conduct to 160 degree. So what it is given is, we know like we are having like the maximum it can go up to pi minus like inversion, that will be equal to 180 minus 160, so R will be equal to cos 20 degree. Also we have, because what is given here, it is being fed through a transformer which is having a transformer ratio of 2:1. That means we'll be having our phase voltage of our 200 volt, that will be because we are having a transformer ratio of 2, that will be equal to 400 divided by 2, that will be equal to 200 volts. Since this is a 3 pulse and M will be equal to 3 for this converter, which will give, if we put these values here, like M will be equal to 3, R will be equal to cos 20, and if we put these values in this equation, V out comes out to be equal to 155.42 volts. Therefore option A is the correct option to the question number 7. Now coming to the question number 8. Here it is given that, like just a minute, I'll move this a bit here. We have a 3-phase to single phase cycloconverter employing 3 pulse positive and negative group converters. Like the question is similar to the previous question, but here something else is asked. So each converter is supplied from a transformer with the turns ratio of 2:1. So the supply voltage is 450 Hertz. We are having a load of 2 ohms, and the impedance offered by the inductor is 1.5 ohm. So what is given, in order to account for the commutation, that is all we know, the overlap and the thyristor turn off, the firing angle in the inversion should not exceed 160 degree. So we have to find out the output power. So like for output power, we know, if we know the output current or output voltage, we can calculate the output power, because we are knowing the like the resistance is given. So in the previous one we calculated our V out. V out is calculated to us. So when we know the V out, we can calculate the I out, that is flowing through the like Had it been like only the resistive, we could have told like P out will be equal to V square by R. But we know here only the active power will be across through the like uh, be through this like resistor active. So when we'll be calculating the I out, it will be equal to V out. We have already calculated, that comes out to be equal to 155.42, and we know the total impedance that will be offered will be square root of R square plus omega L square. So we know R, that is 2, omega L also we know, that is 1.5, that is 2 square plus 1.5 square. When we solve this, I out comes out to be equal to 61.17 amps. So when we know I, we know that the active power will be to the resistor, so we know that it will be equal to I square R. So when we do square of this and multiply that by 2, that is the resistive only, we get the power equal to 7730.22 watts. That means that is equal to 7.73 kilowatt. That means option B is the correct option. Now coming to the question number 9. A single phase voltage controller has an input of 230 and a load of 15 ohm resistive, and what is also given for 6 cycles on and 4 cycles on, determine the RMS output voltage. Here what is given is the single phase voltage converter is turned on for the 6 cycles, and then it is turned off for the 4 cycles. First we'll be seeing how this single phase AC voltage controller will look like. Let us say this is the voltage that is given here. We know when T1 will conduct, we will be getting the positive voltage across the load, and when T2 will conduct, we will be getting the negative. So here you can see, let us say this is like a single phase AC voltage source with an integral control. Like that means we want to control the amplitude of the output by controlling the number of cycles for which will be turning the AC controller. So this is called an integral cycle control. Here you can see we are, let us say this is the source. So here you can see we are giving the triggering, let us say at the 0 point for the T1 here, that in then it is Ig2. So we get the positive voltage, then we will be getting the negative. So it is here you can see it is turned on for the 3 cycles and turned off for the 2 cycles. Then again turned on for the 3 cycles, then again it will be turned off for the 2 cycles. So we have this kind, but what is asked in the question, like we are turning it on for the 6 cycles and turning it off for the 4 cycles. So in order to have for that, like when we have this kind of a thing, we get the output voltage that will be equal to Vs into root of N divided by N plus M. Here M signifies that for how many cycles our device is our converter is turned on, like, and N plus M will be like N will be like for how many cycles it will be turned on, and M will be like for how many cycles it will be turned off. So you can see we know that Vs is given to us, that is 230 volts, and we know V out then will be equal to root of 6 divided by 6 plus 4. You can consider this root of N divided by N plus M some sort of a duty, that for a certain period of time this is on and this will be divided by the total number of the cycles. So our V out will be come out to be equal to 178.157. so if this kind of a question will come out, like you have a input is given, and we are turning on the converter for a certain amount of cycles and turning it off for some certain other sort of cycles, then you can simply use this formula and just put the values and you will get the answer. So the answer to this question is like 178 volts. Coming to the question number 10. SMPS switch mode power supply is used for, A. Obtaining the controlled AC power supply. B. Obtaining the controlled DC power supply. C. Storage of DC power. D. Switch from one source to another. I think you should be able to guess the answer to this question. Can you guess what is the answer to this question? Like we have been like discussing up to the and through this previous number of lectures, we have been discussing this SMPCs. Okay, one of this is like B. So you can see like this B is the correct option. So what is the switch mode power supply? Like we are having an input and we want to have the controlled DC at the output. We want to have the DC, like let us say if we are having a bug, we saw how these switches operate. If we want to have the control DC at the output, then we'll be inserting the switcher network. If we are having a buck operation, we'll be having a switch network in a certain way. Boost operation, we'll be having it in a certain way. These are all SMPC, switch mode power supplies. And what they do, ultimately our goal is we want to have our controlled DC supply. That is the ultimate goal. Like with these switch mode power supplies, what we are able to attain is we are obtaining controlled DC power supply at the output. So option B is the correct option. So yeah, that is for today. Like this completes like the questions that we had to cover today. If you have any questions, like you can ask, or if you want anything to like repeat, then I can do that as well. So if there are any questions, you can type in the questions. So if there are not any questions, then we can conclude our today's session. Thank you everyone. And still like I am here for 5-10 minutes. If one of you have questions, that we can type in.